Good afternoon, everyone. Welcome to the HPL seminar this week. Today, it is my pleasure to introduce our speaker, Danielle Whittier. In 2009, Danielle started her undergraduate in engineering physics at the Queen's University, where she primarily worked on nuclear power. After she received a Bachelor of Science degree in 2013, she came here to the University of Calgary to start her PhD course in biomedical engineering under the supervision of Dr. Stephen Boyd and co-supervision of Dr. Prism Schneider. Danielle's been interested in mechanisms that lead to bone loss throughout aging disease and treatment. She's been particularly curious whether different trajectories of bone loss exist so that better patient-specific tools can be developed to identify fracture risk. This research question led her to work on her PhD thesis project, which is about how to predict fragility fracture in bone using advanced medical imaging and machine learning to diagnose osteoporosis. Danielle is planning to graduate this summer and will be starting her postdoc working with Dr. Ralph Mueller at ETH Zurich in Switzerland, and this will be fully funded by NSERC postdoctoral fellowship. Aside from academic career, she also mentions that she loves outdoor sports, skiing, hiking, biking, and climbing. Today, Danielle is giving a talk entitled as When Will You Fracture? An investigation into predictive fracture modeling using machine learning and advanced medical imaging. All yours.
Perfect. All right, I'll give the share screen there. Excellent. I imagine you can see the presentation now just fine. Excellent. Okay, yeah, thanks for the introduction. Today I'll be talking a bit about a component of my PhD thesis titled When Will You Fracture? This is a bit of a extension to the last presentation I gave for the McHague seminar for those who attended that, which was Are You Destined to Fracture? So there is a lot of overlap, but I promise you at the end we'll have a bit of an extension to that, looking at predicting time to fracture in individuals. Now, just to sort of center what I'm talking about when I mean fracture, I'm talking about fractures that are caused by osteoporosis. So I'm not talking about predicting young high trauma fractures. What we're looking at are ones that are caused by deterioration of bone microarchitecture, reduced bone mass that lead to an increased risk of fragility fractures. So these are fractures that happen if, say, you fall from standing height, by tripping over the rug or gardening. And of course, we don't want these to occur, as they have a lot of negative impacts, both on patients and high burden on our healthcare system. So the current method to assess fracture risk in individuals is using dual energy X-ray absorbed geometry, or DEXA for short, where what we do is we can take an image, a 2D image of something like the hip, so the femoral neck here, and get an output of aerial bone mineral density, which we plot to assess whether someone's in the osteoporotic range, low bone mass, or normal range. However, this tool isn't that sensitive to individuals who are at high risk of fracture, and most people fall in this osteophenic or this low bone mass range. So to address this, numerous clinical risk factor tools have been developed to account for all the other aspects that may contribute to increased fractures or reduced bone quality that aren't necessarily captured by density alone. And the most common of which is called FRAX, which gives you a 10-year risk of major osteoporotic fracture by accounting for these other risk factors that are known to impact bone quality. However, even with this clinical tool to add and supplement DEXA, what we find is that we still struggle to distinguish who is going to fracture, who's at risk of fracturing. So here I'm just plotting DEXA T-score or ABMD, as well as FRAX score of individuals relative to age for those who've had a hip fracture and those who have not. This is from some unpublished data in our lab. And what you can see is it's really hard to separate those two groups looking at either of these plots. We can see there's a general trend of the red hip fracture group here being lower, but to actually be patient specific about it, it's extremely challenging. So of course, in our lab and a number of labs around the world, we've been investigating using high-resolution peripheral quantitative computed tomography, which is essentially a peripheral CT scanner that can get high-resolution images of bone microarchitecture, usually at the tibia or radius. And from this, we can get 3D bone mineral density. We can also get compartment-specific densities, which is very beneficial, along with architectural information from that structure. And we can even go a step further, especially our lab specializes in this, is applying finite element analysis by simulating mechanical load on this bone to get an estimated failure load, so biomechanical properties. So this information has time and time again shown to add benefit to assessment of fracture, but it's been incremental, and a lot of work has been done to try and find ways to improve this. The most notable is the Bone Microarchitecture International Consortium, which is a group that has consolidated a number of prospective fracture cohorts around the world, making one of the largest or the largest fracture cohort there is with HRPQ-CT data for this age range that has high risk of fracture. And so this group essentially aggregated this information and looked at trying to understand to what extent can HRPQ-CT improve fracture assessment. So here, what they found, and they reported this as hazard ratio. So this is the 1, 2, 3-fold increased risk of fracture for decline in these properties. And what they found is here we have the femoral neck, or T-score we call it for DEXA, performs reasonably well. And all of our HRPQ-CT parameters are either on the same scale or perform slightly less when predicting or identifying fracture risk. The one exception being, of course, is failure load. However, what we want to know is the additive performance. So can HRPQ-CT improve beyond what DEXA already does? And so when we look at that and adjust these hazard ratios for our femoral neck BMD or our FRAC scores, what we find is all these factors are attenuated, especially so failure load here, where we see it's highly comparable to what DEXA has for a hazard ratio. So to me, though, this makes sense, as these individual parameters only give us a small snapshot or a bit of information about an individual's bone, and it doesn't really give us the whole picture about the complexity of this information. So for instance, here's some examples of a cross-sectional image of a tibia scan. Here's the grayscale image, where we see these two individuals, these two women, have the same cortical density, but we can see the cortical bone is actually very different when you look at the characteristics of it between these two individuals. One is thick and has quite a few pores, whereas one is very thin and has a lower density on the tissue level. On a similar note, here's two individuals have the same trabecular separation, so the average measurement of separation between trabeculae. And here there's a notable difference in that bone quality is in the trabecular compartment between these two individuals, that's just not captured with this one metric. So there's a need to sort of find a way to aggregate and combine all this information that is quite complex and has a lot of interactions to be able to better interpret extreme CT data, or sorry, HRPQ CT data to improve fracture assessment. And so one tool, from my title, you may have guessed, is machine learning. Machine learning is a very effective tool in identifying complex patterns, often non-parametric patterns in data. And two of the most common approaches are unsupervised learning and supervised learning, which I'll use both of today. Unsupervised learning is where we have data set where we believe there's groupings or clusterings of data, but we don't know what those clusters are ahead of time. And so this is more of a discovery approach where we try to identify these groups using unsupervised methods. On the flip side, a very common tool, especially in medicine, is supervised learning, where we know the groups ahead of time. Say, for instance, we're predicting disease and not disease, and we want to be able to predict that with the information we have. And so we have this labeled data, and we try to guess or estimate a separating boundary between those two with a supervised machine learning algorithm. So both of these are effective depending on the question that's being asked. So my first question that came about looking at these results from the Bomic Consortium was specifically whether unsupervised learning, machine learning, can help us identify groups of these bone properties in the population. So in other words, phenotypes, which are expressions, unique expressions that individuals have based on genetics and environmental factors. And more so, do these phenotypes help provide added insight to someone's future fracture risk? So with this question, I proposed this as another secondary study for the Bomic Consortium, and with support from Doug and Mary in Boston, who are the sort of safekeepers of that cohort, they gave us the data, which we are part of at the Bone Lab, to investigate and ask this research question. So to set this out, I built a unsupervised machine learning pipeline, which I've just summarized in this one visual schematic here, and we'll go through in a bit of detail. But on a high level, the idea is we take the Bomic data set and I perform a two-stage clustering process, which I'll talk about, to identify clusters or phenotypes with using bone microarchitecture data. With this, we then characterize it to understand and interpret what those clusters are or what phenotypes are, and then further assess fracture risk across these phenotypes to see if there's differences. I also perform some external validation to check whether these clusters are consistently phenotyping individuals, but I won't talk about that today for the sake of time. So first, a bit more detail about the Bomic data set that I'll be using. These individuals are individuals, like I said, across North America and Europe from 7 cohorts. And each of these groups have collected health and fracture history information on these individuals, along with HRPQ-CT and DEXA imaging at baseline, and FRAX score calculations from that. And then with that, and here's just a schematic of where those scan regions are for those scanners. Following that, the follow-up was essentially tracking until an event occurred for these individuals. So the event of interest, of course, is a fracture event. But of course, people are lost during the study either to death, loss of contact, or the study has closed at that particular region. And so here we have a mean follow-up of just under 5 years. And here's just a violin plot showing the distribution of average follow-up time for men and women. Now, this cohort was majority women, about 70%. And we see that the age range is quite broad. So we have, or quite broad, but still in that older adult range. So as young as 40 and as old as 90 years of age in men and women. And when it comes to the fracture events, here's just a breakdown of fracture by site. But today I'll be focusing on the major osteoporotic fracture sites. So that's our upper arm or humerus, our wrist or forearm, our spine, and our hip. And so we had about 5% of the population had a fracture at one of these sites, and an additional 5 at any other site that would be an osteoporotic site. And here's just that breakdown for men and women. So with that, I have all this information. So planning what to do and how to phenotype our bone microarchitecture, what I did is I selected and narrowed it down to only the parameters that we collect using the standard analysis with Extreme CT at these 2 scan sites, along with our estimated failure load, and height as a surrogate for long bone length. What I did not include are things like sex, age, weight was not included, or any fracture status for phenotyping. So this resulted in 21 features in total that will be used to identify these clusters. Then when it comes to the actual clustering approach, the idea here, the issue we have is we don't know how many clusters exist ahead of time. So what I did is I took an agglomerative clustering approach to this. And the idea is that this modeling method of clustering does not require prior knowledge of how many clusters exist. So just to give a little schematic of what that looks like, here suppose we have 2 features, so 2 parameters plotted with the data points. And to find clusters, agglomerative clustering works in the way that each point is in its own cluster to start. And then the closest points, which we measure by distance or dissimilarity, are then grouped together in step by step. So here we see that A and B are close together and E and F are together. So we can build this diagram saying that they merge into their own, the same clusters together. And then we increasing our trade-off of dissimilarity to continue grouping all of these individuals, building this tree plot here until we have all data points in the same cluster. And once we have this information and the trade-off between grouping individuals all together and dissimilarity, we can then select a level that makes sense to define our clusters. Often this is called the pruning level when looking at the dendrograms. So I applied this to the Bomic data set. And there are a number of different ways of measuring dissimilarity, just nuances in distance measurements. So I tested a number of these. And here's what those dendrograms look like for the Bomic data set. And what we find is on quick visual inspection, we can eliminate a lot of options and reduce it to a handful of candidate models. And with these candidate models, what I found is consistently three clusters emerge, or three defined clusters end up occurring regardless of the approach. But one issue with agglomerative clustering is that it's a greedy algorithm. And essentially what happens is if you take a different subset of the data, you can get different results. And so it's not the most stable. So I chose, instead of choosing the best of these candidate models, what I did instead was use them as seeds for a secondary stage of clustering. And specifically, I used fuzzy C-means clustering. And the idea being is we get the advantage of identifying the number of clusters and a good starting point using hierarchical clustering. And we use that to seed the centroids and number of clusters into this fuzzy clustering approach, where we then end up with a final model or set of models, one for each candidate approach, which are then compared using interneural validation to assess the quality of the clusters, so how compact they are and separated apart they are, as well as checking stability by doing a subsampling approach to make sure that you are getting consistent results, even if you perturb your data a bit. And so with that, I ended up selecting the top performing model from the 4 candidate models in that way. And so just a bit about fuzzy C-means clustering, if you're not familiar with it. It's very, very similar to K-means clustering, which is probably the most common approach to clustering there is. The caveat being that it allows, in the name of it, it's fuzzy, it allows for overlap in our clusters. So this sort of softens that hard clustering membership approach, where if someone's really on the boundary, instead of forcing them into one cluster or another, we make it continuous. And so the way that works is each individual or each data point is given a cluster membership to every single cluster that ranges from 0 to 1. So for instance, someone that, say this is our fuzzy heat map for fuzzy cluster 1, someone that's down here in these, this feature plot here would have a high membership association, nearly 1 to cluster 1, but relatively low to cluster 2 and 3. If you look here, if that makes sense. And these sum to 1. So it's a very nice way to look at phenotyping, especially for something like bone microarchitecture, where there's sort of a continuum of characteristics that can emerge, but we want to find common patterns that arise. So once we have these final clusters, the next step is to characterize them. And so to do this, I'm going to talk more about just the visualizations rather than the hard statistics that I did. And to actually explain it, I'm going to use something that I've dubbed the bone phenotype triangle. This is not necessarily a typical plot that I am familiar with, so I'll walk you through it. The idea is that because we have these soft cluster memberships, we can actually plot someone's cluster strength, strength to cluster 1 versus strength to cluster 2, for instance. Here I picked 1 and 3. And so what that means is if someone has a high membership to the first cluster, they'll end up here. Whereas if they have a high membership to cluster 3, they'll end up over here. And by default, if they have a weak membership association of both 1 and 3, they'll end up closer to the origin here, which would be our cluster 2. And so then we can see the distribution of our individuals across these fuzzy clusters this way. Now we can look at things like population distribution and a parameter distribution. So the first thing to look at, of course, is where do people fall? So here what I've done is I've taken that plot and just applied topography profiles along it. And here you can see where there's higher density groupings of individuals. And of course, it makes sense. We have higher densities at each of the clusters. But when we split the population by male and female, we see that this clustering approach, even though we didn't tell it sex of individuals, it intrinsically finds those sort of sex differences that we're all very familiar with when it comes to skeletal health. So namely, we see that the male population ends up in this one group primarily, whereas females are spread far more across all 3 clusters, but dominate the other 2. And this is sort of shown if you force the hard cluster membership as well. So we can take this a step further, of course, and visualize different properties using this approach. So here what I'm showing are heat maps applied to these triangles, here for age and femoral neck ABMD. And you can see that age is generally sort of a mixed bag throughout. There's maybe a bit of older age range up here, closer to cluster 1, but pretty evenly spread. Femoral neck BMD, though, we see that we have a lower femoral neck BMD in cluster 1 and a higher one in cluster 2. Now looking at, so we can do this with all of our parameters, and I'm not going to show you every single one, but say when we extend this and look at our compartment specific densities, what we start to see is that we don't get the same trend across the board for wherever we look. And here the idea is just looking at and seeing how our cortical density and our trabecular densities sort of have different signals or are associated in different ways, different phenotypes. And this key continues if we look at microarchitectural parameters, our cross-sectional area, and our failure load. And so this is showing how these clusters are effectively grouping and identifying common combinations of these complex characteristics for us. And from looking at this and looking at partial correlations with all these memberships, I've aggregated this information to sort of summarize what these clusters are best described as. And so to me, they come down to the first cluster is our low density phenotype, where we have low density, we have our healthy, and we have our structurally impaired. So our first cluster where we have low density phenotype, if you look at these grayscale images that are proportionally scaled, we see that generally it's a lower density than our healthy phenotype. And we tend to have a lot worse of cortical bone microarchitecture, so generally thinner and lower density. And these things are all highlighted where we see that here's just a plot of total bone mineral density for these tibia scans. And we see that the first cluster up here has the lowest by far. And that's a really distinct differentiator for this group. The second phenotype is our healthy phenotype. Overall, it's the ideal bones that you probably see in publications that are sort of perfect looking and low fuss, where we see it's high density, we have really rich architecture, where we have very low amount of trabecular separation and all that. And this really comes together and is most evident when we look at something like failure load, where we see it by far has the highest failure load, which is good. You know, it takes more for the bone to fail compared to the other groups. And then finally, this third cluster is sort of our oddball one, or our unique one, where it is notably smaller, typically smaller bones in terms of cross-sectional area. And we see that, in fact, actually, when it comes to things like the cortical properties, it's very similar, and it is really not different from the healthy phenotype overall. It has similar cortical densities and thickness, but where it differs is in the trabecular region, where we see that we start to have higher amounts of deterioration of that architecture. And this one here, I'm just showing the total cross-sectional area. Here we can see that's a really distinct feature of it, is that these are smaller bones, and this is resulting in lower failure load, even if we have a high quality cortical bone. So this is how we've described them. And now the next question is, does this actually really mean anything when we're looking at fracture? It's very interesting academically, but we really want to relate this back. So the next step is looking at understanding how incident fractures spread across these groups. And just to refresh, when I'm talking about fractures, I'm again only talking about our major osteoporotic fracture sites. But I did this analysis with all fracture sites, and the results are very, very comparable and along the same lines. So the way I approached this was using survival statistics, where I first compared between phenotype fracture risk, looking at whether, first looking at using a Nelson-Allen estimator to estimate cumulative hazard relative to the different phenotypes, and then Cox proportional hazard ratios to adjust for different covariates to see if those differences persist. Then after that, I performed a within phenotype fracture risk. So looking at understanding, okay, once we look at a phenotype, within it, are there different imaging biomarkers that help distinguish fracture in that group? Because for instance, not everyone in one phenotype is likely going to be fracturing. So first looking at between phenotype, when we plot these cumulative hazard curves, where essentially this is the additional hazard over time of fracturing, so higher is bad, what we find is that the low density and the structurally impaired phenotypes have significantly higher cumulative hazards than our healthy one. On top of that, they're actually significantly different from one another. So we have different levels of fracture risk, or stratification of our fracture risk. When we look at adjusting these, because these curves are really just raw, they're unadjusted for sex, for age. When we put Cox proportional hazard ratios to adjust for that, and that's shown here, we start with these starting points where these are the unadjusted hazard ratios. We start very high. So our low density phenotype is, about a 5.5 hazard ratio of increased fracture risk relative to our healthy phenotype. After we apply adjustments, we find that this group does dampen notably, but mostly because when we adjust for femoral neck ABMD. So that density is a very big factor in this group. And so if we account for that, of course, we still see that they're at high risk of fracture, but that probably makes up the most major reason why they're at higher risk of fracture. The second group, this structurally impaired phenotype, we end up with a more modest increased risk of fracture relative to low density. But what's interesting is even after all these adjustments, we really don't see it dampen all that much. So it remains relatively consistent. And so things like adjusting for DEXA don't really do anything for this group. And so now the next step is looking at understanding, okay, if we looked within, say, the low density group or within the structurally impaired group, are there unique biomarkers we should be looking at? So not just femoral neck bone mineral density. And so here's sort of the Cole's Notes version of all those assessments, which I'll walk you through. Again, these are just hazard ratios, but now they're for within each phenotype, and they're for each individual parameter that we have. I haven't shown all of them, I've just shown the most notable ones. So when we look at the low density phenotype, this one had very similar characteristics to what the overall bone or the Bomic paper represented, where a lot of parameters were associated with fracture, but the most notable ones were densities. So here we see femoral neck BMD, total BMD of the radius, and trabecular BMD. These are all the highest ones, and even after adjustments, trabecular BMD remained significant in this group. And of course, femoral neck. So this was a strong predictor for this group. And we can really think of this as our classic osteoporotic group. When we looked at next the healthy phenotype, however, what we found is most of the parameters, even before adjustments, were not significant predictors. Femoral neck was somewhat of a predictor, but this was inconsistent when looking at all fractures versus major osteoporotic fractures. And so overall, what we found is the rate of fracture in this group is so low that realistically, medical imaging is at its limits of being able to detect or assess an individual's fracture risk in this group. They have healthy bone. The final group, the most interesting, which probably visually stands out when you look at this, is that the structurally impaired group had a very different imaging biomarker than the others, where we see that failure load is by far the highest predictor of fractures. It's quite high. And even with adjustments for DEXA, it is unchanged. And what's even more notable actually is that femoral neck BMD is not a significant predictor in this group at all. So a DEXA scan doesn't help distinguish if someone's at risk of fracturing in this group, is what that really means. So this is all quite interesting, and sort of summarize all this phenotyping information into one slide. What we have here is a way of visualizing phenotype membership, where we have these three groups. Our low density group, which is our classic osteoporotic group, where density is the best predictor of fracture. And we have the structurally impaired group, where we have generally smaller bones, but the cortical characteristics are normal or good, above average even. So density isn't a good predictor of fracture. Instead, what is more appropriate are the structural characteristics, which are best summarized, which makes sense, are best summarized by failure load. And then finally, we have this healthy phenotype that has overall great characteristics when we look at bone microarchitecture. And generally, we find that they're at low fracture risk, and there's not any substantial imaging biomarker that helps distinguish them because they simply don't fracture that much. So the big question is, well, this is great, especially as an academic exercise, but what can we actually do with this information when it comes to clinical treatment? So my next question ties in to what I mentioned earlier, and is looking at supervised machine learning and asking whether or not this can improve fracture risk by accounting for all this complexity in the data that we've now interpreted. Now, one caveat to this is that supervised machine learning is typically a classification problem where we have disease, no disease. But in this case, and what we've been working with is survival statistics. So of course, fracture studies are observational. We can't test failure of fracture on individuals by pushing them over. So we're limited to just seeing whether people fracture over time. And what's especially complicated with fracture modeling is that we don't know if someone will fracture outside of the study. So say if we lose them to follow-up because they move away or just drop out of the study, we don't know if they fractured in that time, or even after the study's concluded, individuals can fracture. And so this is handled, of course, using survival statistics, some of which we've actually used, and I've used in the latest slides there to show differences in fracture. But it does pose challenges if you're using conventional machine learning. Fortunately, a lot of these machine learning approaches have actually been extended and adapted to handle survival data, so censored data where we don't know what happens. And you can think of essentially any of those conventional classification models most of them have an adapted approach. So for instance, random forests, we have random survival forests, and we have neural networks that handle survival data, and a number of others. So today, just as sort of the exploratory approach to this of asking whether this can help, I'll be focusing only on random survival forests, but of course, the idea would be to extend and look at other machine learning models. So just a brief summary for those who are not familiar with random forests at all. It's one of the most interpretable machine learning approaches, I would say. And it's very handy. All it is a method where we build a number of decision trees. So each decision tree we build to try and best classify an individual based on fracture, no fracture, using, of course, the parameters we provided. So we set thresholds for densities, that set thresholds for microarchitecture, and so on. The reason it's called a random forest rather than a decision tree is because we build a whole number of these these decision trees that are sort of randomized in a way with the parameters, and then typically on the order of hundreds, and then we take a weighted average or a majority vote of this outcome to decide what the final classification is. Here I'm showing this as if it were a classification problem, but I guess the math behind it has been extended to survival prediction, where we're predicting a time to fracture, for instance, rather than fracture or no fracture. So with this approach, I built a simple supervised machine learning pipeline where, there we go, where I've taken that Bomic data set we've talked about and from all those cleaning steps we had before. And then I apply the random survival forest models to this. And from this, what I did is actually I'm comparing it to our clinical benchmarks, so DEXA and FRAX, that I built predictive models using simple Cox regression, just because there's not that many parameters to fit around. And I compare these essentially to evaluate the performance using a few standard metrics, which I'll talk about later. Another thing, though, I took from this random survival forest model is looking at variable importance, which is a very handy aspect of forest models, is that we can actually understand what variables come up the most often in building these decision trees. And so it tells us what is making the decisions effectively for predicting who will fracture and when. And this allows for interpretation and tying back to our phenotypes. So a bit about feature selection. A really nice thing about these random forests is that there's limited pre-processing required or feature reduction necessary. It's good to do, but it's not as crucial as other approaches. But we do also need to keep in mind that we want to be practical in picking our parameters based on the difficulty in actually gaining access to them in the real world. So what I mean is, does it require 2 medical imaging procedures? Does it require extra computation time? Does it require more time at the study visit or say a clinical visit? And so based on this, this kind of mindset, I decided what feature sets will actually be tested and implemented here. So the first one is our minimalist approach, where we take our basic covariates that are relatively easy to capture, or commonly captured, I should say, and we add just our standard HRPQ-CT parameters, so our cortical densities and areas and architecture. The second feature set I implemented was one where we did all these things the same as the first, but added failure load to it, because this adds complexity and just computation time and resources. Then the third model I did was I added on top of this femoral neck bone mineral density, which requires an additional scan. Although if this were implemented, it's likely the scan would have already been available the way that HRPQ-CT would be used today. So I tested these, and the idea was I'd compare across these features in addition to comparing them to the reference performance predictive models that we have that are based on current clinical tools. And to do this, in each case, I took the data and split it 70-30 split for training and testing, and performed a 10-fold cross-validation with bootstrap sampling. So just random resampling at each fold. And this allows for each fold to give you a performance or an output, but then you can get an average and standard deviation performance out of those across those folds. When it comes to hyperparameters, for those who are familiar with random forests, the only one I tuned was the number of trees, and I determined this using the out-of-bag error rate in order to decide what the appropriate number of trees was necessary. All other parameters for now I've kept at the defaults, to keep it simple in this first sort of pass at this analysis. So the first thing that I looked at, say taking the final model, the one that has all the parameters in it, I wanted to look at first understanding what variables are important and how it's making these decisions effectively. So here's a plot, and don't mind this axis right now, but here's a plot of that variable importance ranking, where the higher, of course, this bar is, the higher up it is, the more often it's being used to improve the decision making in these decision trees. Whereas down here, of course, we're seeing that they are not adding or contributing to that performance. And so when looking at this plot and looking at what parameters come up the most, what immediately stands out is our top 3 parameters that really drive these decision trees are the ones that are the imaging biomarkers for our low density and our structurally impaired phenotype. Specifically, we're seeing radius trabecular BMD, radius failure load, which are the 2 best predictors for those 2 phenotypes, and of course, femoral neck BMD. So this is really reassuring. It's showing that yes, this predictive model is actually capturing all that complex information intrinsically and using it to hopefully improve fracture prediction. Another thing I really noticed, which is interesting, is that several of the covariates that we use did not contribute or help at all when it comes to predicting fracture, primarily sex, weight, and height. And I see this actually as a real positive. It shows that once we can look under the hood and see someone's bone quality, we don't necessarily need these clinical risk factors. And things like weight and height, we don't need to measure at a clinical visit. We could actually remove these from the model without impacting performance. So when it comes to performance, the way that I looked at this was using the Concordance Index or C index. For those who've not heard of that before, it is the same as area under the curve, but extended to survival models. But if you were to reduce it to a classification problem, they're equivalent metrics and range in the same way. Another thing I also quantified was the estimated 5-year area under the curve. So although we don't have, we have the survival data, we don't know if people fracture after the study, we can still take these predictive models and predict a risk of fracture at a certain time point or up to a certain time point. And we just need to pick one that is reasonable for the data we have. So I picked 5 years because that's about the average follow-up time of our cohort. And so when it comes to performance, here I've shown a table where we have our reference models with our C index and AUC relative to our HRPQ-CT models with additive information. And what we immediately find is, well, one is we do have improved performance when we jump from FRAX especially to HRPQ-CT, but these are marginal increases, although the differences between FRAX and these models are significantly different. What's interesting, of course, is FRAX actually underperforms when we compare it to ABMD, which is what Bomic found and what is consistently found, which is not reassuring for a tool that is meant to improve fracture prediction. But we see, what's interesting is we see that and this is reflected same within our area under the curve, where we see this a small jump improvement in our predictive models. But when we add additional parameters such as FE and ABMD, we see some marginal improvement. But really, if we're looking at a specific time frame, there's really no change in the performance. So we can really reduce it to a very simple model of HRPQ-CT and likely get all the benefits. So here I've just visualized that 5-year receiver operator characteristic curve, where we have our FRAX model, our ABMD model, and then our HRPQ-CT model, where I've only shown one because they're very similar and overlap. So it would just look noisy if I had all 3. Now, unfortunately, it's not this, knock your socks off kind of improvement, but as a first pass with random forest, which is usually one of the more underperforming machine learning methods, this is a promising approach. This sort of puts the lower limit on performance, I would say, that we can expect from machine learning. Another really nice output or outcome of this is that we get these patient-specific cumulative hazard curves. So from this model, when I predict an individual's risk, risk of fracture using these survival trees, we can actually plot a cumulative hazard where we see essentially the percent risk of having, say, a major fracture over time or at a specific time point. And this is how that 5-year risk of fracture is actually determined. So here's just an example of 2 patients where they have different curves of risk over time. And we would stop and take, say, if we wanted our 5-year risk, we'd stop here and look and see that, say, this individual has a 20% risk of fracture in the next 5 years, whereas this individual has very negligible, less than 1% risk of fracture. So these are very handy in actually producing a clinical tool that can be used for personalized fracture prediction. And so just to close all this up, to kind of bring it all together and explain how this could be used, I'm going to end with a case study example with 2 subjects. They're actually subjects that are in this study. So the information is all real, but although it is, of course, handpicked by me to kind of illustrate the point. So these individuals, if you look at subject 1 and 2, what we have are 2 females, age 70, typical lifestyle or information. Both take vitamin D and calcium for bone health. Both have reasonable levels of activity. Each of them has a different clinical risk factor. So one has no prior fragility fractures, but does have a parental hip fracture, a history of parental hip fracture, which is a common concern due to the genetic characteristics of that. The other has possibly had a prior fracture, but the trauma level is unclear, and they don't quite recall how old they were when it occurred. So it's unsure if this is considered a fragility fracture, or if this would not be something that would be input, say, into FRAX. And otherwise, they have no other clinical risk factors. Now, the question is, how do you manage these patients, and what do you do to decide whether or not they need treatment or additional screening? So say these individuals, you go and get DEXA scans for them, which would be the first step to assess whether there's any concern and they should be put on any treatments. Both come back with femoral neck T-scores in the normal to low BMD range. So just to recall, a T-score of -2.5 or less is considered osteoporotic, and anything higher is low BMD or normal BMD. So they're in these ambiguous ranges where they don't have distinctly certain osteoporosis, but there's still some concerns because of their clinical risk factors. And when we look at their FRAX, though, they get a 10 and 12% score. And these score ranges are in the moderate range. So 20% is considered, and higher is considered high fracture risk. 10 to 20 is the moderate range. So these results are ambiguous. It's very hard to decide what to do. And one of these individuals will go on to fracture. So the question is, how do you decide? Well, what you could do is you could requisition a secondary screening using HRPQ-CT. So go and have a radius and tibia scan to determine if we can improve stratification of fracture risk. So the first thing you get back for this first subject is we find that based on all the parameters that are aggregated, and you're given back a phenotype report where they're in the density deficient phenotype, and they're plotted up here, kind of well in that range. And on top of that, they're in that phenotype, and they also have a very low bone mineral density when we look at their trabecular compartment, or overall even. And that's the major imaging biomarker of concern for this group. So you look further in the report that also produces that predictive risk of fracture using this information, and you look at their cumulative hazard curve, their personalized curve, and you find that at their 5-year risk of major osteoporotic fracture is 16.5%, which is considerably high. And so this person, you can then say, well, they have all this ambiguous information here, but with this HRPQ-CT added information, it's evident that they're at high risk of fracture based on their phenotype and the predictive modeling. Now, going to the second individual, if we look at them and get their report back from HRPQ-CT, we find that they're in the healthy bone phenotype and actually are well in there. So there's not really any biomarkers to consider. And when we look further at the predictive modeling for them, we find that they're at a very low risk of fracture. So 0.7% risk of major osteoporotic fracture. And so when you compare these two individuals now, before they were extremely comparable and very hard to distinguish, but with this added information of bone phenotypes, and especially of the predictive modeling, we can actually very much stratify them and distinguish which one should perhaps be treated or at the very least monitored closely versus one that's not a concern and does not need to go on to further treatment or care. So that's the idea of this information. And the benefit is that on top of just having this percent output, with the phenotyping information, we can understand why. And we can understand what risk factors to look at and to monitor, say, for this individual that's at risk. So that sort of concludes the my presentation. I hope that case study sort of wraps it up and brings it all together for you. Oh, and then, yeah, this is the individual that fractured. Forgot to mention that. But the idea here to bring it all together is that these bone phenotypes using this clustering helps give insight into the characteristics that lead to fragility in a way that's far more intuitive than looking at all the individual parameters. And on top of that, we can extend and use machine learning models to capture this complexity to improve predictive models to assess patient-specific fracture risk. Of course, there's lots of caveats and considerations, and we can leave that to the discussion. I'm curious to hear your thoughts, but I'll wrap up and just thank my supervisor, who's been highly supportive of all this work, along with the Bone Imaging Lab, and then, of course, all the Bomic collaborators who have supported offering advice and feedback and data collection. So thank you.
Thanks so much, Danielle. Yep, for giving an interesting talk. I really enjoyed it. So I would like to kindly encourage everyone to turn on your camera if you feel comfortable with it. I believe we could then see each other and then have a more active discussion period. Thanks for doing that. So if you have any questions for our speaker, please use the icon raise hand button, which can be found if you go click reaction icon at the bottom of your Zoom screen. If you cannot find that icon, that's okay. Please feel free to send me a message via Zoom chat, then I'll call on you when it is your turn. Now I'll open the floor for the questions. Yes, Michael, please go ahead.
Danielle, thanks for the nice presentation. I'm really curious as to why the radius measures from the HRPQC team seem so much more sensitive to fracture risk than the tibia. Do you have any ideas?
Yeah, so there's a few possibilities. I think one of the biggest ones is actually how we collect the data. It's not that the tibia is not sensitive or informative. It's that in this case, I've used standard analysis parameters. So for instance, things like the cortical thickness is automatically measured and indirectly measured in a way. And we know from previous studies or studies that I've done that the tibia has a lot more error in measuring and quantifying things like thickness and densities. So because I've used the automated parameters instead of these corrected parameters, it's likely that the radius that just is less prone to these errors is more effective at measuring fracture or risk of fracture. That's my main belief, but there could be others that are more pathologic.
Yeah, I kind of would have assumed if someone had maybe low density in their radius, they'd have low density in the tibia too, but maybe that's also not the case. And
well, they do. So they looking at all these heat maps and associations, it's definitely pathologic the way that people are clustered. It just seems that the radius properties are the best at actually identifying that increased risk of fracture, likely because they're more accurate and true measures of the individual's bone health.
okay,
yeah.
Cool. Thank you.
Siska, please go ahead.
Hi, thank you. That was very interesting. I really enjoyed it. A very clear presentation. I was interested when you presented those two examples. There was a difference. I mean, you said that their activity levels were quite similar, but this one person was walking between 1 to 5 hours a week, which I would consider not that much. I don't know if you looked into activity levels and if there was any association there with risk.
Yeah, that's a good question. So these individuals were available through the Calgary cohort. We don't have activity level information on the entire consortium, unfortunately. And I say similar, you're right, that they are different, but I would say both of them reported like what they also reflected as moderate or reasonable levels of activity rather than no activity. It'd be interesting to look at that. One big challenge is looking at self-reported information is very subjective, and my experience with self-reported activity is it's very noisy. So looking at something like more direct measures of that, so say through wearables or new apps and whatnot, would be really beneficial in understanding things like that a lot better. But yeah, unfortunately, we can look at this study in detail.
Okay, thank you.
Art, please go ahead.
Hi, I'm interested in the triangle diagrams you showed. And I guess I have one question, which is a little bit just of a suspicion question, which is it just looks extremely clean, and I wonder why the triangle diagrams look so clean, because usually I'd expect some outliers sticking out there, but you have these really clear boundaries to the whole diagram. So is something being cut out there, or is that really how the data looks?
No, that's how the data looks, but it's not that there are not outliers. So the way that those fuzzy clustering membership values work is they sum to 1. So an individual, say, that is exactly in the middle of that diagram would have a 0.3, 0.3, 0.3 membership association to the clusters respectively. So that plot of the triangle, the reason there's none outside of that is because if they were outside of that triangle range, they would sum to greater than 1 potentially. In reality, the fact that we see individuals in the middle there shows that there's not perfect separation between those clusters. If we had perfect clustering, we'd see a clear gap between the tips or the maximas, but we don't see that. So we do see that there's a reasonable amount of ambiguity in some individuals in that middle range there.
I see. So is it my eye that's fooling me when I just see? So it's really the boundary between the data and not data that seems exceptionally smooth to me, and I'm just wondering, you know, shouldn't it be or maybe it's just when you zoom in, and maybe there's so much data there that when you zoom in, you do see that it's pretty jagged, you know, just not really forming a nice clean line as a border.
Yeah, that's true. So that is possible. Okay. Actually, it's a very large data set. So there's almost 6,000 data points, about 5,000, 6,000 data points shown in that one spot. So yeah, it end up smoothing in that way. And then when I was showing the heat maps, that's where I've actually applied a grid to that region and then implemented the color where that's of course being smooth. So it's an average of those regions. So that might be why it's so crisp.
Yeah. And then I guess what I'm truly curious about is, so you have this nice clustering method, and of course everything is very nonlinear, but I'm wondering if you just now use those clusters and yet you just do a say a linear discriminant analysis, how well can a linear discrimination do in just describing what are the relationships, you know, that separate, you know, cluster 1 from 2 or 2 from 3 and things like that, or is that totally hopeless?
That's a good question. I'm not sure. So the closest I can say is I haven't done LDA, but I've done some principal component analysis with these data sets, not this one in particular, but with 2nd generation data sets, and often found that the top principal components relate in sort of a mixed way to actually these clusters. And this was way before I was working on this. But what you'd find is there was principal component 1 was really quantifying low density, and component 2 was quantifying poor architecture. So I imagine they would reflect that as well. It'd just be a different way of sort of approaching them.
Okay, yeah, that's great. Well, I wonder if you could do the principal components first, and then just take your top 3 or top 10 PCs and then do the clustering, and then how much different would that be?
That's a good question. I'm not sure. Yeah, it'd be worth looking at.
Yeah, because that would essentially give us linear combinations.
Yeah.
Okay, well, thanks.
No problem.
Brent, please go ahead.
Thanks, Danielle. I really hope that you're going to submit this as an abstract to ASBMR this year. I think it'll really hit. I think it'll make a big hit, actually. Are you?
Oh, yeah, that's a question to have with Steve. But I think it would make sense to submit, especially the later half of this, when we're looking at building a fracture prediction tool. Yeah, my hope would be to submit this to ASBMR and actually add more to it. So I've only looked at random forests. I haven't tuned hyperparameters in great detail. So the hope would actually be to compare a few different models and get a good performing one.
Cool.
So, yeah.
I think I've talked to you before about sort of Carl Jepson's work, phenotype, different types of bones. So he basically separates bones, actually radius bones, into wide and narrow bones. And one thing that's super interesting when he does this is that, and he looks at changes in fracture strength, and this is experimentally measured in cadavers. And when he looks at changes in fracture strength, narrow bones don't illustrate age-related declines in fracture strength. why do bones do? And he's proposed a few different sort of mechanistic explanations for why that is. But to me, it kind of thinks with the cross-sectional area there that your cluster 3 is like maybe a narrow bone group, and then cluster 1 is this is maybe the wider bone group or whatever. Do you obviously don't have changes over time with these data, but you are somehow, which I have no idea, I don't understand, how you get patient-specific cumulative hazard risks from just one scan of a patient. You'll have to explain that to me at some point. But I'm wondering, do you see a very shallow slope in fracture risk for cluster 3, but a real more steep sort of risk type of curve for cluster 1 that would sort of describe that you're going to have big changes in your risk because of aging?
So yes is the answer. Looking back at those cluster, the phenotype specific cumulative hazard curves that are the average of everyone's individual's occurrences, you see that the highest slope, so to speak, of cumulative hazard is in the low density group. So their bone is likely adapting, like you were talking about with those, who was it, Jepson, I believe? Yeah, thanks for saying that before. It's likely that, that group goes on to deteriorate more, perhaps, and has a higher slope versus the structurally impaired group that isn't increasing their cumulative hazard as much. On an individual level, I haven't looked at individual cumulative hazard curves, but I imagine it'd be similar in that sense, looking at those.
One thing that's cool about the phenotyping is it allows you to sort of ask questions about whether or not these people are fracturing for the same types of reasons, right? Like, like it provides you maybe with some insight into the mechanism of fracture. And so I have this big beef with the extreme CT groups, and that is they're always talking about, I'm going to push the data analysis, and I'm going to show you that it's more powerful than DEXA. Because, right, the argument, the pushback from the clinicians is always the same. It's always, well, finite element analysis doesn't do much better than DEXA, so why should I do it, right? And it's marginal at best if I do it. But like, I think another argument could be that these high resolution images, they give you insight into the mechanism of fracture.
Yes.
And then also an ability to sort of track therapeutic progress in a way that you can't with DEXA. So why, when I go to ASBMR, did I see any of these extreme CT people making that argument?
I'm not sure. Yeah. So I totally agree. And that's sort of the potential of the phenotyping aspect is, I could have just skipped that and done the predictive modeling, but the improvement is marginal, and that's not very exciting. But understanding why individuals have different risk of fracture is very interesting. And there is future potential in looking at longitudinal data and how people progress with treatment if they're in different phenotypes, with age or long-term age and all that. It has a lot of potential to kind of take a different approach to looking at extreme CT data and using it to benefit clinical care rather than just try to outdo DEXA, really. I totally agree. Yeah.
So I don't see any hands up, so I'm just gonna keep going. Is there, okay, Walter, last question, is there any talk about trying to incorporate this type of classification into just another extreme CT output out there in cluster 2?
That would be my hope. So realistically, my vision for this would be that like we have the normatives website where you can upload your HRPQ CT data and it spits out percentiles to help understand the raw numbers. There's no need for the user to change anything about that step. And the idea could be that if you upload your raw data, it'll spit out your phenotype, your fracture risk, and those percentiles and make a nice report. That would be my end goal, this summer, to be honest, to do that.
Cool, super, thanks.
Yes, Walter, please go ahead.
Yeah, thanks, Danielle. I enjoyed the talk too. I was wondering, as a non-bone person, I was surprised that you were saying that the different sites that you're measuring, you might find very different bone quality. And I was wondering why that is. I would have assumed intuitively that somebody has either healthy bones kind of everywhere or not. So why do you think that somebody could have really a bad bone quality at the hip but great bone quality at the ankle? Why is that?
Yeah, so I don't necessarily think that the sites truly vary. I do believe that it's in large systemic, unless there's some reason, like disuse or whatnot. I think it's systemic. I think the challenge is something like DEXA scan gives you a 2D image of your femoral neck, and you get an aerial density of that. The problem is if someone has a thick cortical bone and a small cross-sectional area, their bone is going to appear quite dense on that. And what it doesn't tell you is that they're having deficits in that trabecular architecture. So something like looking at these peripheral sites where you can separate those compartments and look at the density in each of the compartments helps you tell if someone has deterioration in that, say, trabecular region or the cortical region. And that's just something that DEXA can't do. And then when it comes to differences between sites, radius and tibia, there's lots of thoughts between one being a loaded site, one being an unloaded site, which is beneficial. But often there's common patterns in these individuals. It's often systemic, the bone qualities, unless there's something spurious that's happening in that individual.
Can you give me a definition of fragility fracture and give me an example of what a fragility fracture is and what not a fragility fracture is?
It's a good question. So, I mean, there's the easy one. We're saying, say someone falls, most common is, they trip on a rug indoors or stumble and fall, and they land and they break their wrist or their hip from that fall. That's something that the body should or would normally be able to sustain, if any, or hopefully.
So that would be considered, so falling and getting a fracture would be considered a fragility fracture. Yeah. So I was wondering then, if that's the case, and so that's included in your argument, then wouldn't potentially the amount that you fall play a big role in kind of the risk of breaking something? Like here in Chemo, my friends always break bones because they mountain bike, they ski, they mountain climb. So, they continuously have broken bones, whereas maybe other people would not, because they live a very different lifestyle. And yes. So how do you incorporate that?
So hopefully, one thing for looking at the phenotypes and sort of looking at differences in hazard, I did mention I included all levels of trauma, but when I did the predictive modeling, I removed anyone that had high trauma fractures. That all includes sporting injuries, for instance. Yeah. But you're exactly right. So there's an upper limit on what medical imaging can do to predict fracture. You have to have a fall, or almost always, you have to have a fall event happen. And that is a big missing link to all this. And quite honestly, I believe that the way you get that, we have self-reported questionnaires and approaches, but what people consider fall or whether they remember if they fell is really questionable. So what you really need is real-time life data, essentially what people are doing in the moment to be able to capture that and understand if there's patterns. In these individuals, we're not looking at people that are super active and doing sports all the time. We're looking at individuals, often they're in care homes. The most intensive activity they're doing is walking, maybe hiking on modest hikes. So you could actually build in some information if you had their lifestyle data of understanding nutrition during the day, so blood sugars, understanding medication use throughout the day, to be able to predict if they're likely to fall. I think that would actually help improve some of these models. But at the end of the day, it's sometimes falling is a very random event. You can't predict it.
Yeah, it might be a random thing, but I'm actually wondering, if bone health might also be an indicator of neuromuscular health and muscle health, and maybe if you have worse bone quality and maybe less good neuromuscular system, are you also more prone to fall? So that if that the bone quality might actually be a predictor of how many times you fall, and then you fall more often, and then you are more prone to breaking a bone. The other thing I didn't quite understand in your data was when you had these hazard risk curves for the couple of individuals. Then for the one individual, for example, the curve was essentially flat between year 4 to 6, and then between year 6 and 8. It shot up by 12 percentage points. And how does that, I could see if you have kind of steady curve, but how can you have these discontinuous data? How do you predict that?
Yeah, so that is actually honestly a limitation of the data, I think. I'm still learning more and more about this. This is, what we really need is a biostatistician that I can bounce these thoughts off of. But one problem is the reason I looked at 5-year risk of fracture is because the average follow-up time was 5 years in this cohort. I could try to match fracts and do a 10-year risk, but very few people made it to 10 years. And the way those curves are made is it's including only data from people that were still in the study at that time point. So as you continue on, you have more and more people drop out and less data you're relying on. So those models become effectively, less and less stable over time, or less and less reliable, I should say. So that's why you start to see, I believe that's why you start to see that shoot up, is because it's building that curve off of predictive information on a very small subset of people that are left in the data. So that for that reason, I would actually truncate that this modeling into only 5, maybe 6 years. For that exact reason. I don't think that's true curves, I would say.
And just a quick follow-up to an answer that you gave to Brent's question about, can you use the micro CT and the information there in implementing rehabilitation scenarios? And I was wondering, the one patient there that you showed that had this abnormal little hole in the middle of the bone. Let's say you see that. Can you actually do something in a rehabilitation program to address that very specifically, or is that not addressable?
Yeah, it's an excellent question. So that's an area of interest for me, is actually looking at that irreversible bone loss, or potentially irreversible bone loss. In theory, like unless there's some major way of intervening, I don't think you can recover that bone, because there's just no surface for that bone to model on. So that's another really big benefit of extreme CT, is looking and seeing, if you have someone that's at high risk of fracture, but you see they have a giant hole in their bone, is there even any point in putting them on treatment? Like, will it even do anything to help them? And so these are excellent questions, and the hope would be that this phenotyping information and other areas of my research would help establish the tools that can be used to study these things. Using in a lot of cases existing data. We have 2 decades of data with extreme CT. It'd be great to look back on it.
Good, great, thank you.
Would there be any last question for Danielle? If not, I would like to thank Danielle again for sharing her thesis work with us. For the next week's seminar. For the next week's seminar, we will hear from Drew Lawson, and the title of his talk is Lower Extremity Strength Capacity and Landing Strategy in ACL Reconstructed Athletes. Hope you have a wonderful evening, and I'll see you all next week.